So how's everyone doing today? Good? I thought the correct answer was, God, I'm tired. A day full of...
That's why we're here, to actually have some fun.
Yeah, this is the fun one, right? No matter what happens, look at this crazy-ass thing this American brought to this country. Look, I got the super secure American-style plugs and everything. Actually, from an American perspective, the British plugs are overly complicated, which sort of makes sense in a way. That's how you start a talk. You diss your audience. So, welcome. My name is Guy Royse. This is a developer's introduction to electronics. That's me. If you couldn't tell from the previous slide, I work for Redis Labs, where I'm a developer advocate. You can follow me on Twitter. I like having people follow me on Twitter because it makes me feel like a better person. And you can check out my stuff on GitHub. Some of the code here that I've done in this talk and the slides for this talk are all up on GitHub. And so if you go to github.com/GuyRoyse. You go to guy.dev, that's my blog. I blogged for the first time in about 3 years, about 3 months ago. So there is actually something new there. So you can check it out maybe the next year or so. There might be some new content. I'm surely not the only person that does this. Yeah. How many here have blogs that they haven't touched in, yeah, exactly. So one very important thing that I want you all to know is I'm a developer advocate. I've been a software developer for a very, very long time. I've been writing software for about 25 years. But there's something that this says. Any guesses what this is? I am not an electrical engineer. So in the US, they have this idea of a vocational school. So when you're in high school, you can choose to take your last 2 years of high school and learn a trade. And so you can go learn like auto mechanic or welding or vocational agriculture, which is kind of a big deal in certain parts of the US, especially parts where I grew up. And I went there and took electronics because I thought it was interesting. And all my teachers were like, Guy, what are you doing? You're supposed to go off to university. It's like, well, I can still do that. They're not mutually exclusive. And so I went and studied electronics. And I spent a year learning analog electronics and a year learning digital electronics. I was 16, 17, 18. And so I have had training. It was 1989. So, I'm certainly not an expert. I'm a hobbyist, but I'm a hobbyist with some schooling. And so that's where a lot of this knowledge comes from, that and the internet and just practicing and playing and stuff. So, but I'm not an electrical engineer, so there are deep things. There's probably mistakes that I make with how I built these circuits that an electrical engineer will look at it and say, no, the resistor needs to be pull up, not pull down because of this reason that I just am not sophisticated enough to know. But for the hobby level stuff that we're doing, this is fine. The goal, really, of my talk today is to try and get underneath some of the technology you're using. So how many of you have used an Arduino? Or how many a Raspberry Pi? Probably slightly more with a Raspberry Pi. And so you're taking these devices and you're hooking them up to these breakout boards, like these things here. There's several breakout boards here. And they've got components on them, but they've just got inputs and outputs, and you use them. And you don't necessarily have to understand how the board itself works. You can just use the board. I actually have a few of those on here. Some of them might not be super visible, but like right here is a little kit. It's a power adapter I built from a kit. It's a breakout board. That's a relay breakout board. There's some LEDs back there. And so you put these little kits together or you buy a board pre-assembled and you just use them. You don't have to know how they work. So the idea of my talk today is to try and get under how some of these work. Because it's kind of cool, and lots of times things won't work and you won't understand why. It's always good to know that layer just below. That's why if you know TypeScript, you still need to know JavaScript. Because if your TypeScript isn't working, it's like, well, what's the JavaScript thing that's not working here? So it's the same kind of idea. It's why we really, really need WebAssembly. But anyhow, bad analogy. Assumptions. So I'm assuming you played with an Arduino or something like it before. Show of hands shows that's pretty true. If you haven't, an Arduino is a programmable microcontroller, so you can load code onto it and then send voltage signals out or read voltage signals in to control electronic circuits. It's got several different modes. That's what they do. That is right here on the board. I know I don't have video, but it's the thing that's plugged into my computer right now. It's got the blinking light on it. I'm not going to go into great detail about the difference between alternating current and direct current. I'm assuming most of you probably know the difference between a battery and an outlet. Your outlet's going to give you an alternating current. I think it's 50 hertz here in the UK. Is it? It's 60 hertz in the US because reasons. And so that's alternating at that frequency, whereas a battery's just got direct current. And I'm not a physics guy necessarily, so you may have had more physics than me. There's some deeper levels when you're trying to understand how current and voltage and resistance relate to each other and what they actually are at a lower level. I'm not going to go into those details. It's too low a level for this talk. That said, I'm going to talk about the first thing I learned when I took electronics all those years ago, back when actually Reagan was still president. And that is E equals IR. This is Ohm's law, and it shows the relationship between voltage. Voltage is unsurprisingly measured in volts, and it's a representation of how hard, it's electromotive force. It's how hard the current's pushing through the system. It's E for electromotive force. Some people use V for voltage. I learned E, so I use E. You've got current, which is measured in amps, and it's I for intensity of current. It's actually I for however you say intensity of current in French, but I don't know how to say that in French, so I say it in English. But I is current. And you've got resistance, which is measured in ohms. And so current is how much is coming through, voltage is how hard it's pushing, and resistance is how much resistance it's getting. Resistance is resistance. And there's a clever picture that many of you have probably seen that shows the relationship between ohms, volts, and amps, right? So the ohm is sitting there making the tube smaller. Volts is doing the pushing, and poor old amps is sitting there with a bad look on his face. So this is super old. I don't know who created it originally, but shows it really well. I felt like, though, that it did need updated for our new internet age, and so I created a new version. I wish I could take credit for creating this. I actually found it on the internet, but it's just too funny. Nothing explains Ohm's law like Rage Comics. There's also the power law. And power law shows how do you compute power. Power is measured in watts. We probably all have run into this before. And it's really simple. It's just your voltage times your current. So if you've got a 120 watt light bulb and you've got 240 volts coming to it, then that would be half an amp powering that light bulb. So you just do the algebra problem. And with both of these things, you can then do the algebra problems and substitute them for each other. So if you know, for example, you want to know the resistance, and you know the power of the circuit, and you know the voltage in the circuit, then you can say, well, resistance is equal to E squared divided by power, and solve all these problems. So that was the first thing I learned. Actually, the first experiment we did was we took and measured our body's resistance. And so we took a meter, and I measured my body's resistance, and I remember it was a really big number, like 40,000 or 80,000 ohms. So, what's that?
Millions?
It wasn't millions. It was a big number, though. And what the intention of it was, it could have been mega ohms. I can't remember. I should actually do it sometime here on stage, but now it's too late to plan that. But you'd measure it, and then you'd use Ohm's law to figure out how much voltage it took to push 1/4 of an amp through your body, because about 1/4 of an amp is what it takes to kill you. And you do the math, and you come out with a number that's like 20,000 volts, and you're like, car batteries are perfectly safe. Then you had to wet your fingers, measure your body's resistance again, and then see how many volts it took. And you're like, oh, maybe I shouldn't change a car battery in the rain. And so that was an interesting experience, one of the first things we learned. Then we started learning about the basic components and what they do here. So we've got resistors and potentiometers, we've got some capacitors, a diode here. That's a relay and a transformer. These are the ones we're going to talk about today. There are others. And we're going to start with resistors. So resistor is the R in E equals IR. And it resists the flow of electricity. They look like this. They got these little color-coded, these little bands on there that tell you their value. They're kind of a pain in the butt to read, and as I've gotten older, they're hard to see to read. And so I usually just hook them up to my ohm meter and measure them if I can't figure out what they are. And that's easier for me. I should probably get a magnifying glass or something. But they're just little chunks of carbon, and they slow down the the current. And below that, we have the symbol for a resistor, just a little sort of squiggly zigzag line there. The R1 means resistor number 1. The 220 omega, the 220 ohms, that's how many ohms, how much resistance it represents. Generally, well, not generally, what they do with the electricity that goes through them is it turns it into heat. So resistors will get hot if you put a lot of power through them. And they're measured in ohms here. So here's a real basic circuit using a resistor. On the left, we have the schematic for symbol for a battery. If you've ever looked at how batteries work, you got a couple different types of metal and then some sort of acid in between them, makes them work. And so those little symbols there are representing those plates. In this case, it's voltage source 1, 5 volts. So we've got a 5-volt battery hooked up to a 1 kilo ohm resistor, 1,000 ohm resistor. This is probably the most basic circuit you could make. And since we know how much the resistance is, and since we know how much the voltage is, we can calculate the current that this resistor would draw from the battery just by doing the algebra, and find out that this circuit pulls 5 milliamps. That is probably the most boring circuit in the world. What's it do? It turns electricity into heat. But understanding how these resistors work is useful. If you have 2 resistors in a row in series, then their resistance is additive. So we've got 2 1 kilo ohm resistors in a row. We can just add them together. Now that circuit has 2 kilo ohms of resistance, which means that if we ran that through Ohm's law, we would be looking at 2.5 milliamps. And this makes sense, right? If you're blocking the flow of electricity with more stuff, there's more stuff in the way, it's more resistance, it's additive. However, if you put them in parallel, you provide more channels for the electricity to go through. And so it reduces the value of the resistor. So here we've got 2 1 kilo ohm resistors in parallel, and the formula is the reciprocal of the sum of the reciprocals. But in this particular case, there's a shortcut because, and it's a very intuitive shortcut. If you've got 1 kilo ohm resistance path here, 1 kilo ohm path here, but there's 2 paths, twice as much can get through, so the effective resistance is half. And so if you do the math, you find out that it's effectively a 500 ohm resistor if you wire them up in parallel like that. So what if you got a more complex circuit? What would the total resistance of this circuit be? Well, you just subdivide the problem. So here we're adding those 2 together. That makes 2K. These are in parallel. Works out to a very satanic 666 ohms. Not planned. And then if we go ahead and add that, we end up with 1.666K. So you're finding the series and you're finding the parallels and doing the math. And that would be represented with this formula, which is just kind of big. But that's effectively how we're doing that. We're breaking those things into their logical pieces. We're subdividing the problem. It's just like with coding. You subdivide that problem and make it more accessible. So this is where resistors actually start getting somewhat useful. And it's a voltage divider. So one of the things that happens with resistors when they're in series is some of the voltage drops over each resistor. And you can measure how much voltage is across them. And so if you've got two resistors that are the same value, then that 5 volts is dropped evenly across the two of them. And so the first resistor is going to drop 2.5 volts. The second resistor is going to drop 2.5 volts. And so if you look here, we're measuring from here to ground, 2.5 volts. In total, there's still 5 volts, of course. And you can use this to, well, I think the most useful thing for this is for inputs. So certain sensors will create a variable level of resistance depending on what it's sensing. Or I've got a potentiometer here, which is a resistor that you can change the value on by turning the knob. It allows you to create an input. Now, most modern circuits don't use this because they're using rotary encoders, and they're all digital. But this is analog, and it's kind of fun. And so this is the first demo. Will be the first demo. Now, this is proportional, right? So in this case, we've got a 1K ohm resistor and a 1.5K ohm resistor. It's still spread proportional to the resistance. So 2/5 of it ends up on the 1K ohm, 3/5 on the other. And so you can control that. Yeah, here's the potentiometer. Before we do that, yeah, we'll talk about the potentiometer first. So the potentiometer is this little guy here. I know you can't see it. That's okay. You'll see it in a bit. It's a ring of carbon, and it's got a piece of metal on it, and the piece of metal moves. And you've got resistance from all the way along the ring, and you've got resistance from the piece of metal in the middle. And so that allows you to measure the total resistance, or from beginning to middle, or middle to end. And so it can act as a voltage divider. And so if you look at the symbol here, that's what this little arrow shows. It's showing that piece moving through the range of the potentiometer. So here we've got, we're measuring the voltage from this point here to ground. We get 2 volts, 1 volt, depends on where we set it. We can set it wherever we want. So for the demo, I like Rube Goldberg machines, and so I've built something that's a little overly complicated. And I work for Redis, so I wanted to put Redis in there. But what I've done is I've built a Arduino Redis bridge. And so the Arduino's got values that you can set. You can input things into them from software. And it's got values that it can provide, things that it can provide to software. And so the Arduino is loaded with a library called Fermata. Fermata and a node package called Johnny5 allows you to send commands to the Arduino over a serial port, which we've got this Arduino hooked up to. Johnny5 is just a node package. So I wrote a little node application that I call Repola, because it polls Redis periodically to read values and then updates the status of the Arduino, polls the Arduino for values, updates the status of Redis. So it's sort of like a sync button between the two of them. And so all of this stuff is actually running already. So we're going to do a little demo. And so anyhow, so this polls Redis, and it polls, so it's repolling constantly. So it's like the E. coli, I was going to say E. coli, but it's the cough drop. Ricola. This brand of cough drops. So that's the pun. So let's take a look at this thing actually working. We've got, so if we see here the little thing I built, I'm going to go ahead and show a push button working just to show you all the stuff working in concert. And the push button is on pin 13. So if I do set, I say get Arduino pin 13, it's a 0, right? Now I'm going to go over here, and I have hooked up here already a button, and I'm going to press the button. I'm pressing the button. Very exciting. And if I go back over here and see if I can do this, I get the value from pin 13. It's now a 1. If I let go of the button, it's a 0. I'm pressing the button. So all this Rube Goldberg machine works. Hooray! Slightly better demo, right? So let's go ahead and hook up, we'll take this button off here. I've built right here a small voltage divider. It's just two more or less picked at random resistors. And I've hooked them up for black and red for positive and negative. And then I'm taking the voltage out of the middle. So I can hook that up over here. And I can just plug black into here, red into here. And then this goes into white right there. And we can see that that is on pin A0. So if I say get Arduino pin A0, did I do that right? Oh, the power came out. There we go. It's returning a value of 779. It will do that consistently. That's because the input channel on the Arduino takes a 0 to 5 volt signal and turns it into a number from 0 to 1023. If I flip this around, then we should see whatever 779 minus 1023 is, or something close to it. That looks pretty close. So the voltage divider, if we multiply that number, if we did the math to figure out, that number from 0 to 5 volts, it should give us the voltage in the middle of that divider. We're not going to do that math, though. What we're going to do is I think I'm going to get a volunteer from the audience, because pushing the button was kind of hard. But now I've got this potentiometer here. If we take a look at it, it's a really tiny little dial. It's about the size of, I don't know, it's like maybe 5 millimeters. It's kind of small. And so I'm going to go ahead and read the value from that. It's at 223. And if we adjust it to another value, we get another number. And so we can use this to get a number from 0 to 1023. So if I put it all the way in one direction, that's 1023. If I turn it all the way the other direction, there we go. We're at 0. So it's able to take that value. The potentiometer takes a value from 0 to 5 volts and gives us basically every value in between. And so this is a useful input kind of device. There are other sensors that do this. There's thermistors, which based on the temperature change the resistance. You could hook that up with another resistor and then get that to go up and down and use it as part of a voltage divider and then get numbers to come in. So you can turn that resistance into a number that you could use and control through software. Cool. Everyone good so far?
Yeah.
Excellent. Okay. I'm going to talk about capacitors. I don't have any super great demos for capacitors, but the capacitor is part of another circuit here, which we'll go in depth. It's not really being demoed, but this guy right here is the power supply, and he's making use of a capacitor. And we'll see how that works in a very simple power supply. A capacitor is, the simplest capacitor in the world is two metal plates separated by air. They're two conductive plates separated by something that's not conductive. There are some varieties are polarized, some aren't. So you've got like electrolytic capacitors, which have an electrolyte in them, which changes their characteristics in scientific ways that I don't understand, but you can just use them. And they have polarity. They have to be hooked up in the correct direction, otherwise they'll pop. Others don't care. And so if you look at the symbols here, This is one that doesn't care. Like it could be like a ceramic disc capacitor. And this is like an electrolytic capacitor over here, perhaps. And, but they're just those two metal plates. And what capacitors do is they can hold a charge. So if you hook it up to a DC power supply, or some sort of source, it will charge up to its maximum capacity, which is measured in farads. And then it will hold it, like a battery would hold it. And then you can discharge it. But unlike a battery, it charges fast and it discharges fast. There have been lots of people trying to figure out how to make supercapacitors so that we can use them instead of batteries for electric cars, so that we could charge our car in 2 minutes instead of 2 hours. No one's really figured it out yet, obviously, but hopefully they will. They also block direct current because they just suck it up, and then once it's full, it just blocks it entirely. And so if you've got a capacitor in a circuit, direct current can't get through it. But they'll allow alternating current to go through. And there's curves for this, and it's not an all or nothing. It's a little more complicated, but for simplistic terms, for the scope of this talk, we can say that they block DC and they pass alternating current. And I mentioned sometimes they have a polarity. You can use capacitors for two kind of useful circuits. There's what's called a low-pass filter. And what that does is, it's called a low-pass filter because the capacitor it allows low frequency, i.e. direct current, to go through, but gets rid of any alternating current, high frequency, in your circuit. And so the way this works is that you've got this resistor here, it's just your load, current's flowing through here. If it's direct current, the capacitor blocks it, and so it keeps going. If it's alternating current, the capacitor allows it to pass, and it will go this way instead. And so this output then will not have the alternating current in it. So it filters out the alternating current, allows the direct current to go through. You also have a high-pass filter, which does just the opposite. And so here we've got a capacitor at our input and a load here. And that capacitor allows AC to flow, and it'll go right through. But the direct current will be blocked, and it'll be shunted out down to the bottom. As that thing charges, it'll discharge it again. So it blocks the DC. So this allows higher frequency to go through, blocks lower frequencies. Now this is a very simple version of this. If you were to try and build this circuit for, like, say, some specific purpose, like you're doing some sort of audio processing with analog electronics, there's a lot more involved, but this is the concepts behind these circuits.
I think I actually used one of those versions one time when I was actually wondering if my amplifier gave out a high amount of DC current to the speakers while playing.
Oh yeah?
Because then I can just take the DC measure, what's it called? Multimeter.
Yeah.
And you can just measure all of that, even if I'm still playing music, I can measure the actual DC output, because obviously you don't want DC because that will burn your speakers.
Yeah, well, yeah, if the DC output's coming out of a device, if you hook a multimeter up to it, a voltmeter, usually if there's any frequency happening, even if it's net positive, it's moving so fast that your meter can't keep up with it, and so it just shows as a DC output. Diodes. Diodes are like electrical check valves. You got a check valve in your house for your plumbing, where you're pumping water out, but you don't want it to come back. Lets water go one way, doesn't let it go the other. Diodes are the same thing for electricity. This little symbol here is the diode symbol, and it shows an arrow and a block. And so the arrow is the direction that charge can flow. The block means it can't. And so electricity will flow from the anode to the cathode, from positive to negative. Charge will flow. That's probably a better way to say it. But it cannot flow from negative to positive. Now, you might be thinking here that electrons are negative. And so doesn't electricity actually flow negative to positive? It does. But back when they were playing with electricity, they didn't know what electrons were when they first started. And they was like, well, they're different. We're going to call this positive, and we're going to call this negative. And then we guessed wrong. And so all of our symbols reflect the idea that charge flows from positive to negative. even though that's not really how it works. And so this is saying showing positive negative flow, even though it actually works completely the reverse. But yeah, you see here it's just blocks one direction, passes the other. How am I doing on time? I apologize, I just don't have a clock here.
6:10.
What's that?
6:10.
Okay, good. So a diode can be used to turn an alternating current signal into a direct current signal. And it makes sense if you think about it, because your current's coming back and forth, positive, negative, but it is only going to let the positive through. So your sine wave coming in here, you just get the top half, which is actually kind of a neat trick. And you can use that to do something a little more sophisticated. And this is called a full wave bridge rectifier. And it is what that power supply on my board is. And so the idea here is that you can pass in an analog signal, or not an analog signal, I guess it is analog, but an alternating current signal. And when it's on the up, it'll go along the top, when it's going from positive to negative. And when you're on the negative side of that signal, it'll go this way instead. So it can flow one way or the other, but the other diodes keep it from flowing back. And it ends up turning your signal into that. So you're flipping, it's constantly flipping back and forth. And then we've got this capacitor here. And the capacitor charges as the voltage comes across. So we've got this humped back signal. And as it comes in, it'll charge. And then when it goes down, it'll start discharging. And that will smooth your voltage out and give you something that looks a little more like that. Now, in practice, it tends to look more like a sawtooth. But the idea is that you can then smooth off that voltage. And so this is how you build a very rudimentary power supply. This is a transformer. That is represented here. That is a transformer. This particular transformer I got out of a boom box from the 80s, an old boom box. And my friend, I took it into my electronics lab, and we're taking it apart, looking at it, see how it works, and he hooks up to the power supply and then fries my boom box, which I was not very pleased with at the time. But so I scavenged apart from it. And, well, I guess the fact that I still have it says something about me, which maybe I'm a hoarder, I don't know. But a transformer is made up of two coils wrapped around each other. And what they do is they transform your power, or the power in the circuit, from a particular voltage and current to another voltage and current. And it only works with alternating current. So the way they work is that as current flows through one coil, it comes in, and that coil produces a magnetic field. That magnetic field creates a voltage in the other coil and then discharges. Then the magnetic field collapses and they move back and forth. And by changing the ratio of turns of wire between the two coils, you can step it up or down. And so, for example, here we've got 120 volts AC coming in at 100 milliamps, gives us 12 watts. So we've got 12 watts coming into this transformer. This would be a 10-to-1 step down. And we still have 12 watts, but now instead of having 120 volts, we have 12 volts at 1 amp. So there's no power loss. I mean, there's some power loss just because it's imperfect. But in a perfect engineering world, perfect science world, perfect physics world, there wouldn't be any power loss there. And how much there actually is depends on the transformer. This one's old, so it's probably terrible. And so you can use transformers as a way of taking the voltage coming out of your wall and stepping it down. And you can use transformers as a way of taking voltage out of your wall and stepping it up. And so you know how those little power packs you have for everything are heavy? It's because there's wounds of copper wire in those making these transformers work. My favorite transformer is, I don't know if you have them here in the UK, but we call them oil burning transformers, like a fuel oil furnace, burns diesel fuel. And to get that to burn, you need about 10,000 volts. And so they'd have a transformer that would take your 240 out of the house and turn it into that nice high voltage so that you could use it as a spark to burn the fuel oil. And you could get an old one from an old furnace and hook up a couple of pieces of coat hanger to them and plug it into the wall and watch the arc go build a Jacob's ladder. So much fun. Stupid dangerous, but so much fun. Probably the most important component that I'm going to talk about today is the transistor. And a transistor it's actually made out of the same stuff a diode's made out of, usually. There's different varieties. But it comes in two varieties, a PNP and an NPN. They do effectively the same thing, they're just hooked up a little differently. I'm using NPNs, which the bulk of stuff tends to use. But this is a little symbol for it here. And what a transistor does is it's got an input called the base. And the base allows you to vary how much current can flow through the transistor based on how much voltage you put against the base. And you can use that as an electronic switch. So, hey, open all the way up, close all the way down. That is the foundation of every bit of computing technology that we do. And you can also use it as an amplifier by adjusting how much the base is set. So if you go along the range, it will open and close it more widely. Here's a little picture that shows that a little better. We've got 5 volts coming down here. Got a resistor, got a little output here we're looking at. Here's our transistor. There's the base right there. That's the mechanism by which we control the transistor. You've got the collector, that's where the charge collects. And you got the emitter, that's where the charge is emitted. And so perhaps one of the simplest things you could build is a transistor as an inverter. So if we put 5 volts into the base of this transistor, that will allow all of the current to flow. All 5 volts will go down through that resistor and through the transistor. And that output there will be 0 volts. And the reason that will be 0 volts is because this isn't completely correct, but it's sort of a useful way to think about it. You've in essence created a voltage divider because this resistor is going to drop all 5 volts because this transistor isn't providing any resistance. It's allowing all the current to flow. Well, to its maximum. And so if you measure this output here, it'll be 0 volts because this is effectively the same thing as ground. And so this is an inverter. Yeah, here we go, showing that measurement of 0 volts out. 5 volts along the top, 0 volts along the bottom. If instead you put 0 volts into it, the transistor blocks all current, and if I go to measure between here and here, all of it's going to come through here. Because the transistor is blocking all that current. It's effectively got infinite resistance. And so that allows you to take a 0 or 5 volt, a 0 or 1, and invert it back and forth. Of course, you can also set it to a value somewhere in between, open it halfway. In which case, then, your output's going to be somewhere in between those two values. So here I've arbitrarily set it's 3 volts. And then if we flip it, no, I didn't flip it. So that in between allows you to use a transistor as an amplifier. So if you have a more powerful signal coming from the 5 volt to ground here down the line of this transistor, and in the input you put a moving signal, an analog or an alternating signal, varying DC voltages coming in, like this. Then the transistor is going to vary, like it's copying that signal. It's going to vary the amount of current it allows to flow as that signal goes up and down. And then that will create an output that is larger, assuming the voltage along here is larger, or the current's larger, the power is larger. and create a larger signal here. And you'll notice that it's 180 degrees out of sync. It's phased. It's inverted. It inverts the signal. This is a very simplistic way of doing noise cancellation. It's sort of the principle by which that's built on. There's more to noise cancellation than this, but that's sort of the fundamental principle. Here's a simple circuit controlling an LED, which I'm going to demo here. I've got and I didn't show this in all these other examples, but it's a good idea to have a resistor in front of your transistor, because if your current coming in is too powerful, it might not want all that current, and you could turn your transistor into a very burnt out piece of sophisticated silicon. But we've got a 1K ohm resistor there to limit the current coming into that transistor, and then we can control the flow of that.
How do you calculate the size of the resistor?
You need to look at the specs on the transistors, how much they can take, and then how much voltage you're getting out, and you can use Ohm's law then to say, okay, well, if I know I'm getting this much voltage and I only can have this much current, then I can figure that out with Ohm's law. And then you need to know what the limits of the transistor are, and that's going to vary from transistor to transistor. So here we put 5 volts in, transistor lets all the current in, LED turns on. So let's demo that real quick. So we've got here, we got a little LED. It's hooked up to pin, what pin is it on here? It's on pin 5. So let me set that value here in Redis. Set it to a 1, and the LED turns on. You can see here, the LED is on. So we see the red there. If we go back, set it to 0, that light's off now. We can actually, because it's Redis, I can set it to a value of 1 and have it expire in 10 seconds. So now it's on, and 9, 8, 7. It'll go off here real soon, because Redis will delete the key value, and then it'll be null, and JavaScript will treat the null as 0. There, so it just went off. I actually kind of want to have it explicitly set to 0, though, so let's set it back to 0. And that little circuit board there, if we look at it, you can see here. Come on, focus. There we go. The lighting isn't perfect here. Let's try this. Oh, that's way better. So you can see there's an LED, there's a little resistor. It's 220 ohms, and then we've got a little transistor on there as well. It's a PN2222 transistor. So it's a really simple circuit to make. And one of the reasons why you want to make this with an Arduino is that the Arduino tends not to put out a lot of power on its digital outputs. And so this is acting as a power amplifier. If you had a bunch of these hooked to the Arduino, you'd start getting some issues with not getting enough power to these. They wouldn't glow as brightly. And it might even affect the functioning of the Arduino. And so having that little amplifier in there makes it more reliable. I've actually got some here too. This is kind of fun. The Arduino has this idea of pulse width modulation. Have anyone heard of that? Fiuga? The idea is that you set the LED from 0 to 5 volts, but you blink it, but like stupid, ridiculously fast so that you can't perceive it. And if you do that half the time, let's say 10 kilohertz, then it looks half as bright. And so it's a way of dimming an LED. And so on pins 9, 10, and 11 here, I've got a pulse width modulation set up for these. And so you can give it a value from 0 to 255 for how much of that time you want to do it. So if I set pin 9 to 255, see the red one there lights up, refocus. There we go. Let's do the blue one. The blue one is actually easier to see. I think the blue is, set the pin 9 to 0. There we go. So you can see the blue one's lit up there. If I set it to 127, that should be about half as bright. So it does, it's a little hard to tell on the screen, I think, but it is about half the brightness. If I set it down to like, say, 35, it's very dim. And here it is back up at 255. So much brighter now. Let's set that back to 0 so we're not constantly looking at it. So the last thing I'm going to show here is a relay. A relay is a switch, allows you to control a circuit as well. It's actually much older technology. It was originally developed for the telegraph industry because they have these big, long DC runs, and over time, you couldn't transmit that power enough, and so they create another circuit. And a relay is a electromechanical switch. It has a magnet right here, a coil, an electromagnet, and when that electromagnet turns on, it physically moves the switch and completes the circuit. And so this electromagnet has to be a direct current circuit, because that's how electromagnets work. But the circuit it controls doesn't have to be. And so this will allow you to control AC devices, AC circuits, from digital circuits, from direct current circuits. And since we have an Arduino, it's all direct current. We can actually control this night light right here. This is a night light that I stole from my children's room for this talk. It's not that terrible. They're all teenagers now. It's not very bright, but we'll be able to see it on camera just fine. And it's plugged into, right here, we've got this nice metal electrical box. I've got a switch on it just in case things get dangerous. I can turn it off. And it is hooked up to this relay board. And so we can use this to control that AC circuit. It's also good for controlling high voltages or high power from lower signals. So in your car, when you turn the key, you could have power from the battery going straight up your steering column to the key. And then if there's a problem, you get a shock. Or you can use a relay that controls a lower power circuit that's safer to deal with, and then it triggers the higher voltage circuit. So you can also use these for safety. They probably could have used these on the Star Trek Enterprise. Every single time they get struck, one of the panels blows up. It's like, or you could use like a relay or a fuse. You know? But that's not as dramatic, right? By the way, this is completely an aside, but has anyone seen any of the videos of they've taken like the footage of the Star Trek like space turbulence stuff, except they've taken all the motion out of the camera, and you see what they're really doing? Oh my God, they're so hysterical. If you haven't, go check them out when we're done. So here's a simple circuit. This particular one has the relay defaulting to open, or defaulting to closed. So when you push this switch, it will trip the inductor here. It'll create an electromagnet. It will pull the switch down. It will close the circuit, or it'll open the circuit so that it defaults to on. You can turn it off. It's an inverter, in a sense. So you push the button, activates the electromagnet, switch moves. And here it says it completes the AC circuit, but my diagram is showing that not to be true. It's actually uncompleting, it's breaking that circuit. But they're really simple devices to work with. There's actually a little bit more going on, though, that you want to do around a relay when you're using them in your circuit. Now, this breakout board does all this for you. But on this breakout board, there is a transistor, there is a diode, and then there is the relay. And the reason for this is that when you bring that 5 volts in, well, there's two reasons. One, you need the transistor because getting that electromagnetic signal to trip from the Arduino, it doesn't have enough power to do that effectively. So you need that amplifier again. The same reason we have the amplifier on the LED. We want to get an appropriate amount of current there. So the transistor is being used as an amplifier. So 5 volts comes in, the transistor opens up, allows all the current to flow from 5 volts to ground. That goes through the relay, the electromagnet activates, click, the relay clicks. And the lamp, which I'm using a resistor here to represent because Fritzing didn't have a good lamp symbol, then is turned on. So whatever your load is, gets turned on. In our case, this would be the night light. Then when you go to turn it off, when you go from 5 volts to 0 volts, you've got a slight problem. Because the transistor blocks all current, and so voltage stops flowing, current stops flowing from 5 volts to ground. And so that electromagnet has this magnetic field around it that's not being sustained by current anymore. So it collapses. And when it collapses, it discharges in the opposite direction. It's like blowing up a balloon, and then when you let go of the balloon, the air comes out the opposite direction. This is a very similar idea. And if you don't have anywhere for it to go, it will find somewhere to go. And that somewhere will be through your transistor. And could burn your transistor out because I just hooked it up with a bunch of power backwards. And so you put a diode in here. They call it a flyback diode. And it allows the current to discharge through the diode. And so then it can safely be turned into heat and not ruin your transformer or your transistor. And so this is a slightly more complicated circuit. It's not super complicated. And this board right here, it does just that. Yeah, the relay deactivates, magnetic field collapses, diode provides path for the induced current to discharge somewhere. Gives it a place to go. So let's do our last demo here. So here we've got this nightlight, this relay board. And that is hooked up to pin 2 on the Arduino. So if I go to set Arduino pin 2 to a 1, if you listen closely, you'll hear it click. You hear the click? It's kind of satisfying, honestly. Click. Yeah. I actually want to build a binary adder with all these relays so that I can hear it click while it does all the math. I just think that would be fun. But you can see that when I set it to a 1, the night light comes on, right? You can't see that. There we go. The night light is on. If I set it to 0, the night light goes off, it's off. If I set it to 1, give an expiration of 10, it's now on, and in 10 seconds it should turn off. 10 seconds might have been long. It was long. There we go. So you can see it going off. So that's pretty much all I have. I've got a schematic of this entire board here. This is like literally a circuit board because it's a piece of plywood. But this is a basic schematic of all the things that I've shown here put together in one with the Arduino. And yeah, that's pretty much all I've got. I can take questions, or you can go and come up and just gawk at the circuitry if you'd like. How much time do we have left for Q&A? 2 minutes? Okay. So, but we're last, so we can go long. No one cares, right? It's like, no, I want to go on the boat now. So, anyhow, so that's what I've got. Thank you very much. And again, you're welcome to come up and take a look at all this stuff and play with it and ask me any questions.